Everybody, let's take a look at 36 through 40. In this test, it just so happened that most of the questions were actually really straightforward, but I'm going to say that until we're really polished, we'll try to save 36, 37, and 38 for when we have time to do them. All right, let's jump in. A stick on the ground is 3 feet and 6 1/4 inches tall, and it's going to cast a shadow that is 1 foot and 3.4 inches long. How tall is a building that casts a shadow of 40 feet and 9.2 inches? Okay, so the idea here is that we want to do similar triangles. And the important thing here is when we're working with this problem, we're going to be dealing with significant digits. Anyways, so as I was mentioning the significant digit scenario, when we convert those, the conversion factors are going to have infinite precision, and we're really just counting the significant figures of the digits or given to us in the problem. So the 3 feet and 6 1/4 inches is going to have 4 significant digits: the 3, the 6, 2, and the 5. And then the shadow it casts is going to have 3 significant figures: the 1, 3, and the 4. So I forgot to write out the full expression, but when we have similar triangles, the ratio of the height to the base, rise over run, is going to be equal to both of them. So we're going to do a rise over run calculation, and we're going to solve for that. And I apologize I didn't write it, but I'm not able to write it at the moment. But I think we've done a couple of these. Otherwise, we'll go over it in class or in person. Let's continue with 37. 37 is a type of question that we've been skipping, but is actually really easy. These exponential growth and decay questions. And they're usually going to involve 2 steps. So they tell us a person inhales a single virus cell, and the virus triples in number every 4 hours. If it takes 300,000 virus cells to cause symptoms, what is the virus incubation period? So to be able to answer this question, we need to know how to write exponential growth or decay. So some future amount is going to be some original amount times the exponential function e to the x, and it's going to be raised to the power of a rate times a time. And we're going to do this in 2 steps. Usually they give us a time and the quantities, and we find the rate. And that's what's going to happen here. They tell us that the virus triples from a single virus. So the initial amount is 1, the final amount is going to be 3, the ratio is 3. 3 equals e to the r times 4. From here you could throw it into your solver, or recognize when you take the natural logarithm of both sides, you can bring down the powers. Natural log of e becomes 1, so it becomes natural log of 3 equals 4 times 1, so times the rate, and then we divide the 4 over. So now we have our rate. The second step is using the rate and the request of the amounts to get the time. We start out with a single cell, and we will have sickness when that cell multiplies into 3,000. So we apply the equation again. In this case, we plug in the rate from before into this equation, throw it into the solver, or do natural logarithm tricks again, and then from there we get that the time is in minutes. The question wants our answer in hours, or days actually, so just be mindful of that. To divide by the appropriate conversion factors, to go from minutes, we divide by 60 minutes in an hour, and then 24 hours in a day. Let's continue with number 38. The Washington Monument is an obelisk composed of a tapered cross section, which is a frustum of a period, surmounted by a square base pyramid. The frustum bases are 16.8 meters and 10.5 meters respectively, with a frustum height of 152.4 meters. Last thing is the pyramid base is 10.5 meters and it is 16.76 meters tall. Calculate the volume of the Washington Monument. And in this case, it gives us the volume of a pyramidal frustum. And so in this case, this question is relatively straightforward. They give us all the side lanes. We calculate the volume of the frustum, and then we add the volume of the square pyramid. The formula for a square pyramid is going to be 1/3 the base area, which is going to be 16.8 squared, times the height, which is going to be the 16.76 meters tall. I didn't get a chance to write that part down. I apologize, but we can go over it further in detail in person. Let us continue with number 39. We have our inscribed triangle. In this case, they give us the radius and they want us to find the side length of that triangle. Well, whenever we have the radius, we can go ahead and say that that radius is going to equal the area of the triangle over the semiperimeter. The quick way is to set the area, in this case of an equilateral triangle, it's going to be equal to side squared times square root of 3 over 4. And that's always going to be the case for an equilateral triangle. So we're going to load that into the top part of our expression. Now the semiperimeter is the perimeter, which is the side length multiplied by 3, and then divided by 2. So we throw that bad boy into our solver, which in this case I wrote x down here, but understand that that is the same thing as the side length here. I apologize for the lack of consistency here. Okay, but this variable, the side length of the triangle, as well as for the area as well as for the perimeter, these are the same term. Let's continue with 40. Number 40, they want us to find this side length over here. Now in this case, we are very fortunate. This is a very straightforward question. Law of cosine says that this opposite side is going to be equal to this side squared plus this side squared. Hey, that almost sounds like the Pythagorean theorem. And it's kind of like the Pythagorean theorem, except the law of cosines has a correction factor for the acuteness or the obtuseness of the triangle, which in this case has an angle of 117.1. So the rest of the correction term is minus 2 times A times B times cosine of the angle creating side C. And so here's the expression. Thankfully here we can crunch this straight through and get our answer. Don't forget to square root at the end to get the value of C. Thank you again.